Hello, good day. My name is Fernando Alayola, and I will present a poster of the work called Application of Metal Organic Frameworks in Gasoline Desulfurization Processes. Currently, there is a great demand for reliable methods for the reduction of sulfur compounds in gasoline, such as thiophene, benzothiophene, dibenzothiophenone, etc., in order to reduce air pollution and meet established limits. Gasoline, which comes from the catalytic cracking of crude oil, contains high concentrations of sulfur compounds, usually between 200 and 7,000 parts per million. Although the limits imposed vary according to the country, the European Union established the maximum at 10 parts per million, and the United States has a range of between 30 and 80 parts per million. One of the reasons for the removal of these compounds is the contamination of certain catalysts, whose function is to remove other contaminants gasoline has, such as nitrogen compounds. In order to fulfill with these regulations, gasoline is subjected to a catalytic hydrodesulfurization process in which organic sulfur compounds are converted to hydrogen sulfide in order to be removed in an easier way. However, during hydrodesulfurization, olefins are hydrogenated, which leads to a loss of octane and a high consumption of hydrogen during the process. Alternatives have recently been sought to improve or replace catalytic hydrodesulfurization. A viable alternative is adsorption using porous materials for the removal of sulfur compounds. However, adsorption needs to be highly selective for sulfur compounds and not for other compounds found in gasoline, such as paraffins, olefins, and aromatics. One of the porous materials that has caught the eye recently are metal organic frameworks, which consist of a molecule with a metal center surrounded by organic linkers. Due to the disposition that the linkers can have, a structure with high porosity and a large surface area is obtained. Recently, the absorption of behavior of MOFs with sulfur compounds such as thiophene has been studied, where it was observed that some of these were capable of absorbing sulfur compounds even in the presence of other compounds. Therefore, this work seeks to synthesize and characterize MOF74, magnesium, and nickel, and evaluate the absorption of a sulfur compound named 2,8-DB-DBT in an isooctane solution. Microwave-assisted synthesis was used to synthesize both MOFs, MOF74 magnesium and MOF74 nickel. The reagents used for MOF74 nickel were the following: 2,5-dihydroxyterephthalic acid for the linker and nickel 2-acetate tetrahydride for the metal. The conditions used were a temperature of 100 Celsius degrees, a time of 90 minutes, and a potency of 600 watts. For the MOF74 magnesium, the reagents were the following: 2,5-dihydroxyterephthalic acid for the linker and magnesium 2-nitrate hexahydride for the metal. The conditions were a temperature of 125 Celsius degrees, a time of 90 minutes, and a potency of 600 watts. For both cases, the result was a powder with a yellow color. The characterization techniques used were X-ray diffraction, scanning electron microscopy, and thermogravimetric analysis. The characterization results for both MOFs were the following. For X-ray diffraction, the experimental diffractograms of both MOFs coincided with the respective simulated diffractograms on the 2 theta degree values. For the scanning electron microscopy, both MOFs had a crystal size of approximately 1 micrometer. For the thermogravimetric analysis, the MOF74 magnesium is stable up to 400 Celsius, and the MOF74 nickel is stable up to 250 Celsius. The surface area of the MOF74 magnesium is 1,250 square meters per gram, and the 74 nickel 1,010 square meters per gram. For pore size, 74 magnesium had a pore size of 1.1 nanometers, and the 74 nickel had 1.4 nanometers. For the absorption of 2,8-DB-DBT, the MOF74 nickel was used. A solution of 2,8-DB-DBT and isooctane was made, and the MOF74 nickel was added to it. The readings were made with a UV spectrophotometer, and the results were the following. In the first graph, we can see the 2,8-DB-DBT concentration over time, and one can observe that there wasn't any reduction of the concentration. So it was concluded that from 0 to 118 minutes, there was no change in the concentration. There was no absorption. So a new solution was made, a solution consisting of isooctane, 2,8-DB-DBT, and MOF74 nickel, which was added. This time we use 24, 48, and 72 hours for the readings. And the UV spectra can be observed in here. As one can see, there is not really any difference between the three spectra, be it 24 hours, 48, or 72. The three of them are almost identical. The isooctane with analyte and MOF didn't have any difference between times. Thus, it was concluded that even at 72 hours, there was no absorption of 2,8-DB-DBT by the MOF74 nickel. MOF74 magnesium and nickel was synthesized successfully. The characterization by SAM showed an average crystal size of 1 micrometer for both MOFs. The thermogravimetric analysis showed that the MOF74 magnesium is stable up to approximately 400 Celsius and the MOF74 nickel up to approximately 250 Celsius. The absorption experiment showed that there was no absorption of 2,8-DB-DBT by the MOF74 nickel, which was attributed to the size of the molecule, which is greater than the size of the pore.